So last time we did an example with a steep slope and a gate, and now we need to take a look at what would happen if the slope was mild. So if we've got water moving along a channel, and we did the analysis, and there's a gate, and we did the analysis, we would find that critical depth would be shallower than normal depth. And due to this contraction coefficient, we can actually ID what this dimension would be. So if this dimension is h, then this depth right here is h times a contraction coefficient. And so that point is sort of defined. And then if we wanted to do a delta x calculation, then we would need an M3 curve to a hydraulic jump, and then it would go straight to normal depth. Let's take a look at how this works in the specific force and energy diagram. So mostly we're interested in the specific force diagram. So basically, if the gate goes up, this depth goes up, or if the gate goes down, then the depth goes down. So we can control the depth at this section D. And if we plotted out the specific force diagram, it would look something like this. Where critical would be the minimum specific force. And so, and then if we went downstream to the normal depth and we plotted that point, so let's just do some idea thinking, right? So let's just throw out some possibilities. So let's say that h is relatively small, and that means that the depth at section D is relatively small. And so in order for that to happen, then the water would need to build up. It would need to get deeper on this side. And so this would be an M1 curve. So as we lower the gate down, the depth upstream of the gate gets deeper. That's pretty intuitive. Also, the water racing underneath the gate gets faster, which means that it has more momentum. We can see that in the specific energy diagram also. As we lower the gate, moving, say, from this point to this point, we increase the energy. That also corresponds with an increase in the depth on the upstream side. Just as a reminder, these two depths are alternate depths. And so if this point is fixed, given the depth at D or the height of the gate, then it's directly related to what's going on upstream. And so the energies at section D and at section G are going to they're going to be the same. And so you can see how as we lower the gate down, you need more energy to pass the water flow, and that means that the depth upstream of the gate needs to go up. So this is pretty intuitive. So now what we need to do is take a look at what happens as the gate moves with the specific force. So let's say that we have the gate really, really low. So let's call this scenario 1. So the gate's really low. This is scenario 1. And so what's going to happen is during this section of the M3 curve, we're going to be burning off more energy than what we're gaining because the slope's relatively mild. And so what will happen is momentum will reduce because the depth is decreasing, right? So if we're burning off energy, then the depth is increasing. And at some point, it will jump to the conjugate depth, and that's normal depth. So we could call this point right here, we could call that J. And so that would be this point right here. That would also be J. Okay, and if we raise the gate a little bit, not too much, but just a little bit, maybe we're here, that's section 2. So it would need to burn off less energy. And so what that would mean is that this delta X section, that's the section we would be moving from section D to section J in our delta X calculation. That would be getting smaller and smaller as we raise the gate. And so as we raise the gate, the hydraulic jump is getting closer and closer to the gate. At some point, if we raise the gate enough, our momentum as we calculate it at section D would actually be less than J. And so what that means is that there's no delta X. Essentially, the hydraulic jump has pushed back, and it's now an incomplete jump. It's not a total jump. It's just the water is pressing against the gate. And so when you do a calculation for a gate with a mild slope, what you need to do is at section D, just take a quick look and see what is the momentum at D. So if the gate's too high, the momentum at D will actually be less than the normal depth momentum. So here's the normal depth momentum. And so in that case, there's an incomplete hydraulic jump. Essentially, there's no delta X calculation to be had.